Ready to roll. All right, so we're going to start in this chapter, chapter 11, with vectors. And many of you have seen vectors if you've taken physics. Some of you might have had it in pre-calculus. We're going to deal with vectors in two-dimensional space at first and then jump to 3 dimensions. And we're going to see it doesn't really matter what dimensional space you're in. The common numbers associated with a vector, like its length and its direction angle, those things you're going to find are pretty uniform regardless of whether you're in 2 space or 3 space, or even in n-dimensional space. If you're going beyond Calc 3, Calc 3 is all about doing math in 3-dimensional space. Linear algebra is all about doing math in n-dimensional space, so you don't limit yourself to just 3 dimensions. And all these definitions in calculus extend. It doesn't matter that you're in 3 space. You know, in 2 space, you had ordered pairs. 3 space, you have ordered triples. 4 space, you have ordered quadruples, etc. And then in linear algebra, we talk about ordered n-tuples. So you just have every point has n coordinates, and you can still do all the math. You can still find the angle between 2 vectors in 5-dimensional space the same way that we find the angle between 2 vectors in 2-dimensional space. You can find the length of a vector in 12-dimensional space the same way you find the length of a vector in 2-dimensional space or 3-dimensional space. So that's really cool that it extends so easily. Of course, the hard part is the geometry, trying to visualize, especially beyond 3 space. Okay, so a vector is a quantity. It's got magnitude and direction. Magnitude is another word for the length of the vector. So you'll hear people talk about the length of the vector, the magnitude of the vector, and a new word that you'll hear is norm. You'll hear people talk about the norm of a vector. Same thing, it means length. So we have 3 words. All of them mean the same thing when we're talking about a vector. Magnitude, length, and norm all mean the same thing. Usually we talk about the initial point and the terminal point, or the tail and the head, and we write the vector with the initial point first and the terminal point second. And typically in textbooks, they will just use a bold V. Let's see, I don't have one right there. Typically in a textbook, they're just going to write a vector with a bold letter U, V, or W, typically. But when you're writing it on paper, you can't really do that, so we put the little vector symbol above it. But if you see a bold letter in a textbook, 99% of the time it's a vector. So really important to be able to distinguish when you're dealing with an ordered pair or a vector. Those are 2 different things. There's a very close relationship between them, but they are 2 different things. Ordered pairs and vectors are different. Okay, the 0 vector is the only vector that has no magnitude. The 0 vector is just a point, right, because there's no magnitude to it. And we write it 0 with the little vector symbol above it. 0 vector. Here's vector v. You can take a vector and you can scale it. You can scale a vector by multiplying it by a real number. So we call that scalar multiplication. So in math and in science, typically we refer to the real numbers as scalars. Okay, so this vector v is being multiplied by -1. The geometric effect is that the vector does not change in length, and it changes in direction by 180 degrees. So if this is vector v pointing that way, vector minus v just points in the opposite direction, but it's the same length. 3/2 v, we've scaled v by a factor of 3/2, so we've stretched it another 50%, but it still points in the same direction. So scaling a vector does not change the direction unless there's a minus sign, and then it changes it by 180. 1/2 of v points in the same direction, it's just half as long. These 2 vectors both are 1/2 v. This kind of gets at the fact that there are an infinite number of representations for any vector. So if somebody says 1/2 v, you can imagine it anywhere. It doesn't have to be right here. It doesn't have to be right. These are all the same vector. There's an infinite number of representations for a given vector. The representation that emanates from the origin, that's called the standard position. So if you have a vector where the initial point is the origin, then we say that vector's in standard position. But otherwise, you can be anywhere you can imagine. You can put it wherever you need it. You need to put it. Anywhere you need it. Okay, so this just says that, this talks about scalar multiplication here. And if you multiply by a positive number, it stretches it, doesn't change direction. Multiply by a negative, it flips it. And then two vectors are parallel if they are scalar multiples of each other. So you can have vectors that point in opposite directions. Those are scalar multiples of each other. Multiply by -1. So vectors are parallel if they point in the same direction or they point in opposite direction. Then they're parallel. And then two vectors are considered equal if they point in the same direction and they have the same length. Then they're equal. They're the same vector. Okay, we use the word equal. Maybe it's better to use the word equivalent, but people always just say equal. In terms of combining vectors, i.e. addition, if you want to add two vectors together, the way that you add two vectors together, let me make sure that thing is moving. You can either use the triangle rule or the parallelogram rule. And again, it usually depends on the context. Sometimes the triangle rule makes more sense based on how the vectors are. Maybe you're doing a navigation problem and you've got the direction that you're heading and then the direction of the wind. So maybe it makes more sense to put your vectors in a way that they share a common initial point. So if this is the direction you're heading in a plane, that's the direction the wind is blowing. Put them that way and use the triangle rule. Totally fine. Or maybe for whatever reason you want to use the parallelogram rule. You can put your two vectors that you're going to add like that. I guess you're still putting them with their initial points together, but you're going to form a parallelogram instead of using the triangle rule. Either way, I guess this I got to stand back here for a second. Here we're adding u plus v, so I should be doing it this way. So here's v, like the direction you're heading in the plane, and then the wind is blowing on you. So here you're going to use the triangle rule, and you get the resultant vector. They'll use the word resultant when they just mean u plus v. Resultant. It's just the sum of the two. So either way, if you're starting with u and v, you can put them with the same initial point. So here you can imagine flying that way and the wind is blowing that way and you end up going in that direction. Same idea here. You can move this vector v wherever you need it to be. Wherever you need it to be. Doesn't matter. Has anyone not added vectors before? Is this new to a couple people? So triangle rule, parallelogram rule. Parallelogram rule tends to be a little bit easier to conceptualize. You just line the vectors up with their initial points, and you form this implied parallelogram, and then draw the diagonal through the parallelogram. Tends to be a pretty convenient way to think about adding. Subtracting, on the other hand, is a little bit weird. So let's take a look at this. So again, let's get clear in our head that we're starting with vector u and v. So we've got this vector u, we've got this vector v. Those are the two that we're starting with. And we just got through talking about how if you multiply a vector by a negative, it just flips it. 180 degrees, does not change the length. So this is a picture of negative v right there. V is pointing that way, negative v is just pointing the other direction. And then if you look carefully at this, this is actually lined up just like the triangle rule, where those two can then be added. U plus negative v, and then we would complete the triangle to get u plus negative v, and we're going to call that vector u minus v. If you're dealing with the parallelogram rule, let's do this if we're imagining parallelograms. Man, this feels so low. All right, so let's suppose we take these two vectors right there, and we wanted to find u minus v. So let's call this u, let's call this v. So minus v is going to point just in the opposite direction. And let's use, I think that's a vector. So there's minus v right there. OK, so if we were to add these two vectors together using the parallelogram rule, we're just going to draw the implied parallelogram. So that implied parallelogram is going to come this way, there, and there. roughly. That's really hard to, that looks a little more parallel. Sort of like that. And so if we want to combine those two with the parallelogram rule, then we're just going to draw the diagonal of the parallelogram. So the diagonal of the parallelogram is going to come right up through here. So that is going to be u minus v. U minus v. And notice that that vector right there, that's the same vector as this right here. We could have just put that vector in right there. That is also u minus v. So the point I'm trying to make here is that if we start with our two vectors aligned, right there, if you just connect the two and put the arrow in the right direction, that's the difference of the two vectors. U minus v is right there. Make sense? Or do you have a question? That one's u. That one's v.
Is there a reason why we're messing with negative vectors right now?
Just so that we can define what u minus v is. So when we have these two vectors right here, if we connect those two, we get u minus v. If we drew the parallelogram out there, then u plus v would be across that diagonal. So u plus v is going to be across one diagonal, and u minus v is across the other diagonal. That make sense? Haley?
You said vectors are equal if they're the same direction and magnitude.
Yep. Same direction, same magnitude. So this vector right here is u minus v right there. So that one must also be u minus v. So if they have the same direction and same magnitude, then they are equal. So if we wanted to draw u plus v on here and make a total mess of this picture, u plus v would be coming out like that. So u plus v is going to be the diagonal of that parallelogram over there, but that's a total mess, so we're not going to leave it on there. So if you draw the parallelogram, one diagonal is u plus v, the other one is u minus v. And we use the negative v just in order to define what subtraction of vectors is. So that's why we need that scalar multiplication defined first. Okay, now we're still just combining vectors in a very abstract way. We're not in a coordinate system. We need to introduce a coordinate system if we're going to start doing, lots of different types of problems with them. You need a coordinate system if you're going to be solving any real useful problems. So what we're going to define are the components of a vector. And the components of a vector basically give you directions on how to get from the initial point to the terminal point. The components of a vector, the first component and the second component of the vector, notice those are in angle brackets, not parentheses. So those mean vector components as opposed to point coordinates. So those are coordinates, those are points. And this is called the component form of a vector. And this gives us a little roadmap. It tells us how to get from the initial point to the terminal point. Those aren't coordinates. Those tell us how far to go to the right, how far to go horizontally, and how far to go vertically from the initial point. So
is one of them angle and one of them magnitude?
no, they're both, neither one of them is angle. They're both, the components, the magnitude of a component tells you the horizontal distance, and the magnitude, or the absolute value of the other one tells you the vertical displacement.
Mm-hmm.
So here, let's look at this picture. Okay, so, for example, this is vector v in standard position, because vector v is emanating from the origin, so it's in standard position. So in this particular case, let's imagine we're in quadrant 1, so v1 and v2 are positive. Let's get that case done first. So here, do you agree that the coordinates of this point are also whatever those numbers v1 and v2 are? Right, so if you have your vector in standard position, the ordered pair of the terminal point and the components of the vector are the same. But if you move your vector out here away from the origin, well, the coordinates of this point here are definitely not v1, v2. Right? You've moved it further out into quadrant 1. But you haven't changed the vector. You've just changed the coordinates of the terminal point and the coordinates of the initial point. This distance right here, this horizontal distance, that distance right there is still v1. And this vertical distance is still v2. Everybody agree with that? So the v1, v2 components of the vector, they're telling you how far to go horizontally and then how far to go vertically to go from the initial point to the terminal point. So it's a little directions on how to get to the terminal point from the initial point. But when you're in standard position, the two coincide. The components and the coordinates of the terminal point are the same. And that gives you insight into how ordered pairs and vectors, how they are similar. Anytime your vectors are in standard position, they're identical to ordered pairs, essentially. All right, any question on that concept? So this book calls this a position vector. Usually, there's a lot of books that will talk about a position vector a little bit more generally. This book, when it says position vector, it means that it's coming from the origin. Most books are going to throw the word standard in there to emphasize that it's coming from the origin. This book will just talk about a position vector and imply that it's coming from the origin. In the terminology I'll tend to use if we're dealing with a vector that is maybe not at the origin, if we have two ordered pairs and we want to form the vector between them, I'll typically refer to it as the displacement vector. If we've got 2 points and we want to figure out the vector between the two, I'll usually call it a displacement vector. As we go through, if you have questions, of course, ask. So let's introduce the coordinates. So we're in a Cartesian coordinate system. And we have a vector over here, and you can kind of see that, okay, if we move this vector over there, the v1 distance is really, this v1, the value of v1 is really whatever this, the difference in these x coordinates right here. And the v2 number is the difference in the y coordinates. Now, if we weren't in quadrant 1, we'd have to be a little bit more careful, right? Because here, we're in quadrant 1. We know that y2 is greater than y1 because of the picture. We're in quadrant 1, right? So we can do that. That works out fine. If we're in different quadrants, we might have to think a little bit more carefully about it. But it will actually work if we just, as long as we subtract y's and subtract x's, it will work if we do it in the right order. If we do the tip minus the tail. If we always start at the terminal point, and subtract off the initial point, corresponding coordinates, it will always work. So if you remember that it's terminal minus initial, it will always work, even if you're in other quadrants. You don't need to look at any more geometry. And the length of the vector, the magnitude of the vector, the norm of the vector. Obviously, we have a right triangle, so whatever this number is, whatever that number is, we could take the square root of the sum of the squares, and we could get the length of the hypotenuse. So a little right triangle stuff there to figure out the magnitude, or the length, or the norm. So here they're just drawing a correlation between the symbols. When we use the single absolute value bars, that typically is the distance between two numbers on the number line. And this book does the same thing for vectors. If you look in, certainly all the books I ever saw until recently, instead of absolute value, they would do a double absolute value like that to represent. So if you're looking at another math book or a physics book and they use double, it means the same thing as absolute value. That's been a change recently. Recently, these books are just putting absolute value. The idea being that absolute value means distance. Right? Absolute value means distance to the origin if you're on a number line, and here it just means distance from the terminal point to the initial point, the length of the vector. So in old books, though, you'll see the symbol that way. not that it really matters. Okay, so any questions on how you would find the magnitude of a vector? Does that make sense to you? Take the square root and sum the squares. All right, so let's look at this example I have up here. So what are the components of the vector from -2, 5 over to 3, 4? Usually helps if you want to draw a picture, not terribly important for this type of problem. And once we get into three-dimensional space, probably give you more headache than it's worth to try to draw a picture. But this is just a rough sketch is helpful. So we're going from -2, 5 over to there. So rough sketch. So the thing that we need to know is that if we want to form that displacement vector, let's call it V. If we want to form that vector, we're going to do the terminal point minus the initial. We're going to do the tip minus the tail. The tip of the vector minus the tail of the vector. And so we're going to use angle brackets to indicate that it's a vector. Another thing that's changed in the last few years is that some books will not always put angle brackets around their vectors. They'll just say, they should be able to tell if we're dealing with ordered pairs or dealing with vectors, and they'll just use parentheses. So sometimes if you're looking at other resources, maybe online or something, and you'll be like, wait a minute, that doesn't have angle brackets. It's from the context that they're expecting you to determine that it's actually a vector and not an ordered pair or something. So be aware of that too. That in this class, I'll always put the angle brackets to make sure it's just extra emphasis. We are dealing with a vector. I don't want you thinking, is it a vector or is it a point? That makes it clear that it's a vector. So we do tip minus tail. So we're going to do 3 minus minus 2. So the change in the x's and then the change in the y's. So this will give us the displacement vector between those 2 points. So our vector is then, our vector in component form is this. And so again, that's a little roadmap that tells you if you start at the initial point and you want to get to the terminal point, you're going to go over 5. 5 is the displacement in the x direction, and then you're going to go down 1. That's the displacement in the y direction. And let's get this guy out of there. And if we wanted the length of this vector, again, this book will just use absolute value of v for magnitude. So we now know we've got a right triangle. The side lengths, the leg lengths are 1 and 5. So we're just going to do square root, sum squares. So that will be the magnitude of the vector from -2, 5 to 3, 4. Simple enough? Magnitude and component form of the vector. So we will have another form of a vector called the algebraic form, which is the form that they typically use in physics. We'll get to that in a little bit, but just throwing it out there. In physics, they would tend to write this vector as 5i minus j, if you've had physics. In math, we tend to like the angle brackets. You don't have i's looking like j's. You don't have j's looking like i's. It's obvious that it's a vector because of the angle brackets. Sometimes when you use algebraic notation, it can get messier. OK, so magnitude of a vector, just talked about that. We've got another one down here to do as an example. One of you guys try to find the length of that vector. Yelp if you need help. So we'll be taking our break roughly 2 o'clock each day, 10-minute break. So we'll take a break after we finish this problem. Yes, exactly. So if you wanted to draw that vector, it would make the most sense to draw it in standard position, so it's going down to 24. Yep. All right, let's see. So the length of this vector, if we call this vector v, so if we say v is 4, -2, The length of v we simply find by squaring, adding, take the square root, simplify the square root, and that's the length of our vector. 2 times the square root of 5.
For first in class problem.
Woo! Did anyone get it wrong? All right, let's take a 10-minute break. If you did get it wrong, come in and you need help. Let's do it over the break. Oh, off and rolling. Yes, so this equation right here, we have the components. So we're squaring that component, adding and taking the square root. This formula is for if you didn't have components and you just had the coordinates. So if you were given coordinates at 2 points, so if you were given with this situation,
And I was like, well, I'm not an engineer either, but
How you doing?
this
I'm
point,
building it,
let's
not
say, is
you.
1 have a 1.
Yeah.
and
It's
this
funny,
point
so he
is
finally emailed me. He was like, I need help.
Then you would plug in.
So,
Oh, now you
so
want
that's a little bit
Now you
different.
want
That's
to
what this is
and I was
representing
like,
here.
we're locked.
So if you have this horizontal distance, you do 4
Oh my
minus
gosh,
1, you
zero.
get 3.
I'm
So
on.
you do this vertical distance, 2 minus 1, you get 3.
Oh.
So the components there would be 3 complements.
Technically,
This
try
vector
that.
would be 3
Figure out a
complements.
way to.
And then define the magnitude that you put that into.
Sum of squares, yep. Yep. That's right. Yes. If you see any others that you think might be typos, ask. Any questions before we start going on with a couple more examples? Pretty good so far? Starting off.
I have a quick question.
Oh, sure.
I have cookie in my mouth though, I'm sorry.
You have what in your mouth?
I have cookie in my mouth,
Oh.
I'm sorry. So
Cookie question.
when we're doing this, like I just went straight to like the magnitude is of this. Like I can just, I don't have to show that I was like, do I have to do like notation like this is the vector?
No, no, no,
this,
no.
and
That's
this?
totally, yeah, you can just,
Okay.
yeah, that's totally fine. What you have there is fine. Let's talk about adding vectors when we have component form. So the geometric way to add, you line up the vectors and you do the parallelogram rule, or you line up the vectors and you do the triangle rule, if you're adding vectors. If you have components, it's even simpler. If you're adding 2 vectors and you have the components, what do you think you do? Add. Yeah, it's amazing. So we add the first components, add the second components, and we're done. And the picture here is just sort of showing why that works. If you look at vector v here and you take its x or first component, you take vector u, its first component. If you add them, that's actually what you get if you do the parallelogram rule. It's going to give you the same exact value. And then this one down here, if you add the x components, you get. So here we have -5 plus 2.
Oh.
There's a minus sign in there.
Yeah, there's a minus.
Yeah.
Adding, yeah, I use the word maybe. Okay, so 3 minus 2 for the y components, so 3 minus 2 is 1. So that would be the component form of the difference, or the component form of the sum. Component form. This one here, we're just taking the vector -1, 3, and we're going to scale it. So we're multiplying a vector by the scalar 4. And all that means is that we have to stretch the x's and stretch the y. So we multiply the 4 by both components. So the 4 is going to distribute to the first component, and it's going to distribute to the second component. So scaling a vector is done by scaling each component. So you're multiplying each component by whatever that scaling factor is. All right, so for the most part, that stuff that we've done so far, it's not super abstract, not super technical. When we start getting into unit vectors, this is where all of a sudden it feels like you have to think a little bit more carefully when we're dealing with unit vectors. So first off, let's make sure that we understand what a unit vector is. A unit vector is just a vector that has a magnitude of Yeah. All right, let's take a break. Yeah, perfect, right? Unit vector is a vector of length 1. So in physics in particular, you often deal with these standard coordinate unit vectors, I and j. And if you were in 3-dimensional space, you'd also have a k, ijk. And you could write this vector up here as 12i minus 5j. So that's the algebraic form of it. Again, in math, we usually avoid that. You don't have to deal with vector symbols. You don't have to deal with i's looking like j's and j's looking like i's. So we usually don't do that. But that's how you could do it. You could write it as 12 times the unit vector I minus 5 times the unit vector j. Let's put in the components just to see that, oh yeah, that actually is just a different representation. If we put in the component form for I and j, and then we distribute the 12, and we distribute the negative 5, we get back to where we started. We get what we would hope to get. And we end up right back where we were. Yeah, because if the two notations don't align, that's worthless. If you're going to have two different notations, they better line up. So again, component form, algebraic form. All right, so here we go. This is the first sort of trickier piece down here. All right. So let me start with that vector that we have up there. What did I end? What was that? 12, negative 5. All right, so let's come over here. 12, negative 5. So that's a vector, and we know, let's call it vector v. We know that the length of this vector is found by taking the square root of the sum of the squares. So we get 169 in here, which I think is 13 if we take the square root of it. So that vector has length 13. And the question is, first question is, okay, we can visualize this vector. We should be seeing it down in quadrant 4. We're going over 12 and then down 5. It's down there in quadrant 4. The idea is that, is there a way that we can scale that vector back so it's still pointing in the same exact direction, but it only has a length of 1? This is going to be a really important skill for us. We're going to use it throughout the whole semester, this idea of converting a vector to a unit vector and then possibly scaling it by some other factor. There's all sorts of reasons that unit vectors will be important. One important reason is that on the unit circle, if you imagine translating that unit circle into the land of vectors, you can imagine unit vectors that point to the edge of the unit circle. And that's going to be important. And here's what we do. Notice what happens. If that has vector length, if that vector has a length of 13, notice what happens if I divide both components by 13 and then take the length of that vector. So I scaled it. I multiplied it by 1/13. So I shrunk that vector, and let's just see how long this new vector is. Well, we would take the square root of the sum of the squares. So we're going to take the square root. We square this one, we get 144 over 169. We square this one, we get 25 over 169. We add that together, we get 169 over 169, which is 1. So we've created a vector of length 1. We haven't changed the direction because we multiplied by a positive 1/13. When you multiply by a positive number, you're not changing the direction of the vector, you're just changing the length of the vector. So we multiplied each of these components by 1/13. So that's how we are going to take a vector that's not a unit vector and turn it into a unit vector. We just divide each component by the length of the vector. All right, so here, and that's what they're giving us in this notation up here. They're saying that there's two possibilities. You can divide v by the length of v, you get a unit vector. You could also divide v by the length of v and then multiply by -1. That still will be a unit vector. You divide by v, the length of v, or the length of v times -1. Just point in the opposite direction. Someone's trying to come through the wall. Find a unit vector in the direction here. All right, so we're going to take our vector and we're going to first find the length of it. So the length of this vector 5, -2. We're getting good at this. Square root, sum of squares. So we have 25 plus 4. So the length of this vector is the square root of 29. And then the unit vector, I'll just write it as v divided by the length of v. That is going to be the vector 5 divided by the square root of 29, comma, -2 divided by the square root of 29. That is our unit vector. That's the unit vector that we're looking for, right there. Any questions on how we found that? So that points in the same direction as 5, -2. It's pointing down into quadrant 4. All we did was shrink it. We found the length of the vector and then divided that length into each component. Any questions, or is that good? All right. This one, slightly different. Find a unit vector in the direction opposite of 3, 4. All right, let's first find the length of this vector 3, 4. So the length of vector 3, 4, square root, sum of squares. All right, so that vector has length 5. So if we want to find a unit vector in the direction opposite, this vector right here, 3/5, 4/5, that's going to be a unit vector pointing in the same direction. So if we want a vector pointing in the opposite direction, multiply by -1. So we put a negative in front of each of those. And we now have a vector of length 1 that points in the opposite direction as the original vector. So that's the vector we're looking for. This is the vector you are looking for. That vector. All right, you guys try this one. Find a vector of length 6 in the direction of -1, 6. Extra little twist in this one. Let's see if you can figure it out. Vector of length 6. Oh, you did? Oh, yeah. That's fast. Get it. I see it now. I worked twice through these things. Now I see it. Good. Excellent. Cool. Yeah, yeah. All right. It's a good sign when the back row is finishing fast. Very good sign. Perfect. Yeah, good. All right, all right. Doesn't seem as big of a mystery as I thought it might be. Okay, so let's go ahead and walk through this slowly just to make sure everybody's on board. So we're starting, we'll call the original vector vector v. And we're going to first find its length. So the length of vector v, the absolute value of vector v, will be the square root of the sum of the squares. We get that. So when we take vector v and divide it by its length, this is giving us a unit vector. So -1 over root 37, comma 6 over root 37, that's a unit vector. If you wanted to confirm, if someone said, hey, this is a unit vector, the way you confirm that, square, square, add, take the square root. Squaring this, you get 1 over 37. Squaring this, you get 36 over 37. Add them, you get 37 over 37. So that's a unit vector. And now the cool feature that the leap, well, it's not a big leap, I guess, but the leap is that we now multiply by 6. If we multiply that by 6, if you take a unit vector and you multiply it by a scalar, you end up with a vector that has length equal to that scalar's absolute value. So if you have a unit vector and you multiply it by 6, you get a vector of length 6. If you have a unit vector and you multiply it by 10, you get a vector of length 10. If you have a unit vector and you multiply it by -2, you end up with a vector of length 2. So this vector here is going to be the vector that we're looking for. So this vector has length 6 and points in the direction of -1,6. Yeah. Well done. Any questions on that? Any step there that you are not sure about? One thing that I'm very happy with is this new projector. It looks very crisp to me. Can you guys see back there okay? Yeah, remember last semester we had a projector that was like dying halfway through the semester. We could barely see the board. Ah, so nice. Nice and bright. All right, any unit vector questions? Unit vectors. All right, applications. So this book is, in my opinion, if you read especially these navigation applications, it can get a little convoluted. Let me try to give you a summary of the way I think it's helpful to think of this. So in all these problems, whether you're dealing with a boat or a plane, you're going to have the direction that the boat or plane is heading. And so that's what the instrument panel says. It's the way, if you're swimming across the river, it's the place you're looking. It's the place you're heading. But we all know that the place you're heading doesn't necessarily coincide with where you end up if there's a current of some sort, whether it's wind or water. Okay, so this book has some terminology that I find a little bit confusing at times. Velocity relative to the shore, velocity relative to the water. When they talk about velocity relative to the water, they're basically talking about the speed of the boat or the plane in still air or no current kind of thing. They use W to represent velocity of either wind or water. And so here they talk about velocity relative to the shore, and they use V sub G. I assume they're using G for ground. Not sure. If I think back into pre-cal classes, typically what we think about is 2 words, course and heading. And those words I feel like are pretty clear to most people. Heading is the direction that you're heading. And then you add in your current, whether it's water or air, you add that to the direction you're heading, and you end up on your course. You end up in the direction that you're actually ending up. You know, the course that the land, you know, the course over the ground, if you imagine a plane. You know, so if the wind is blowing this way and you're aiming that way, you're going to end up going over here. So the course is where you end up after you've added your direction and the current together. And so that's the basic principle in your head, is that course is going to be the direction you're heading plus the current. And the letters that they use don't always totally line up with that. I personally would sort of think about the velocity of the course equals the velocity of the heading plus the current, which we can continue to go with there, W. That's fine if you think of W as wind or water. You know, a lot of books will just talk about course and heading, and they'll do something like this. You know, that's also possible. Whatever works for you, but that's the basic principle. You've got the direction you're heading, you've got your current, you add those two together, and you end up on a course. Does So the course is the direction you want to, if you want to get to point B, that's your course, but you've got to change your direction to get there if there's current. Okay, so let's see if we can piece this together here. Water in a river moves south at 10 miles per hour. So let's write that as a vector. And so this is the current. We're thinking about this as the W, or the water. So water is going to go south. So that means there's no x component, and we have a y component of -10 if we wanted to write this as a vector. So 0, -10. That would be our water. And then the motorboat travels due east at a speed of 20 miles per hour. So due east. So we're going that direction, 20 miles per hour, so we'll call it 20, 0. And then we just have to decide which is which here. Is this the course or is this the heading? Let's read the last sentence to see if we can all piece it together. They say that 20 is relative to the shore. Bless you. So determine the speed and direction of the boat relative to the water. Okay, so we need to decide whether this is going to be our course or our heading. Which should it be? So the motorboat travels due east at a speed of 20 relative to the shore. So if you imagine the shore, it's ending up, right? It's relative to the shore. It's ending up at 20 miles per hour relative to the shore. So that's sort of after the consequence of the current. So we're going to think about this then as heading or course? Course. Because that's kind of where we're ending up, right? So it says it travels, it's actually moving due east. So that's a pretty reasonable assumption to piece it together that way. You could also, and this is where I feel like I have a little bit of a difficult time with the way they word things, couldn't you also say that it's traveling due east? Couldn't that also sort of mean that when they look at the instrument panel, it's saying east? And so that's actually the heading, right? You could interpret it either way very, very easily. And so what I will do when I write the test, is I'll be really clear on find the course or find the heading given the conditions. Because I feel like you could make a pretty reasonable argument for either of those cases. So the question really is, does this word travel, is that sort of where it's ending up? Is that where it's actually at after the current? Or is that what the instrument panel is saying? It's traveling east. So, like if you're flying a plane and you're traveling east, same thing, I guess. You have the same sort of ambiguity. So if we assume that this actually means the instrument panel, bless you, let's do it that way. Let's assume that means the instrument panel, that the boat says it's going east. If the boat says it's going east, then we would put that on the heading. If the boat says it's going east, then that would be H. Does that make sense? If the boat says it's going east, if the instrument panel says it's going east, then the current's going to affect the way the boat is pointing, and we're going to end up on the course. So if we assume that, so here we assume that travel equals heading, we're going to do it one way. So if it equals heading, then we're going to call that H, and we're going to end up with a course equals the sum of the two. It's going to be 20, -10. And I guess we don't need to do it both ways. If you say, oh, the travel means the way that we're ending up, it's course, yeah.
I disagree with you.
Okay.
I think it's 2010.
You think that
For the course, it's 2010. Positive 10.
positive 10. Okay, so that's if we interpret it the other way. So if we interpret it, so do you agree that if we interpret this as the heading, we're going to do heading plus when to get -10?
Yes. Yeah. That's what Jay.
Yeah.
I get
So
you
if we
now.
interpret it the other way, that it's where we end up, that, okay, we're going along the shore, which is a totally reasonable way to assume it, then we're going to end up with the is it Omar?
Yeah.
Omar. Then we're gonna end up with 20 positive 10. So let's do write it out since you just brought it up then. So if we imagine travel means the course, it means where we are ending up, then it's going to be a little different. Then we're going to say we're going to have course is going to be equal to, it's always heading plus. Oh, and I'm putting that to be course though, so it's going to be 20, 0 equals. So we're going to go this way. We're going to go 20, 0 equals the wind plus the heading, and then we're going to end up subtracting. And if we subtract, we get 20 minus 0, which is 20, and we get 0 minus 10, which is 10. So we just have to be aware that it's a little fishy. If you're doing my math lab and it feels ambiguous, look at the view and example just to make it clear. Are they talking about course? Are they talking about heading? And on a test, I'll definitely be clear whether it's course or heading. Now, in either case, it's not going to matter if we wanted to find the velocity along the course, in this case, or the velocity of the heading, we just take the square root of the sum of the squares. That part's, and we'll end up with the same number with either. Square root of 400, so either one will have a square root of 500. We'll get 400 plus 100 in either one. And we could make that 10 times the square root of 5. And I forget what the units were.
Miles per hour.
Miles per hour, thank you. So here, the velocity of whichever one you interpret it as.
Fast boat.
Fast boat. Yeah, it's a fast boat.
Where is it?
Depends if you're rowing.
22 miles per hour.
If you're rowing, that's a really fast
Actually,
boat.
I was thinking 500.
I don't know if I would want to water ski behind that boat. All right, let's keep on trucking. Let's do one of these guys. Bring in some trig. So we've got a 500-pound load. It's suspended by a couple of chains. What's the magnitude of the force that each chain must be able to support? Now, the first thing we notice is symmetry. So that means the force that the chain needs to be able to hold on the left is the same as the chain on the right. So let's call that force F. And I'm not going to put a vector symbol over it. One common thing that we will see is that notationally it's really convenient to do this, to represent the magnitude of the force F with just the letter F without the vector symbol over it. So here, vector F, and here, scalar F. Everybody follow that? So on this side, we're thinking of this as a scalar. And then the F in here, of course, is a vector because it's got the vector symbol over it. So we're saying the length of vector F is scalar F. Notationally, it's just nice and simple to sort of do that. It's very convenient. So if you're trying to find the length of V, you can just call that scalar V. So it's an easy notational thing. There's times where you prefer the scalar. Like if you're dealing with the length of the side of a triangle, you want it to be a number. All right, so this force here, we need to be able to write. I'm going to call this one over here, I like to just use L and R as the left force and the right force. So the magnitude of the left force is capital F, the magnitude of the right force is capital F. So we have to add these together. And this, let's call it the weight, W for weight. Not wind or water, weight this time.
Do you want this in newtons, or are we leaving it in pounds?
We'll just leave it in pounds.
Okay.
Yeah,
It just seems weird that they would give it in pounds.
I know.
I'm so
I know.
used to
The math books, some of the physics applications are going to be a little bit like that, you know. And well, what is the unit of? Anyone know the unit of mass in our imperial system?
Slug.
Oh yeah, that was fast. Everyone know that? Unit of mass in the imperial system is a slug.
Yeah, you actually
Plug?
mentioned it in Calc 2, I believe.
Oh, is that where we? Oh, did we talk about that? Calc 2? That's possible.
I know.
Talk
we
about
did.
slugs in Calc 2?
I think so.
All right. So here's what we're going to do. This is an equilibrium. If it's an equilibrium, those three forces all added together better be 0. And I'm adding vectors, and when you add vectors, you get another vector. So if these are all 0, what we mean is not the number 0, we mean the vector 0. So if it's an equilibrium, not moving, the 3 added together must all cancel each other out. All right, beautiful. Now what we need to do is convert each of these to component vectors. The obvious one is weight. That one we can do pretty easily. 0, negative 500. That vector's pointing down. So 0, negative 500. That's the easy one. Left and right are a little more difficult. We just got finished doing something that helps tremendously, though. We know that if we have a unit vector and we multiply it by a scalar, we end up with a vector that has magnitude equal to the scalar that we just multiplied it by. So if we can create unit vectors that point in each of those directions, and then we multiply them by capital F, which we're letting represent the magnitude, that would give us the component form of each of those vectors. So left vector is going to be the magnitude times the unit vector pointing in that direction. The unit vector pointing in that direction, if that's 45 degrees right there, we obviously can kind of embed a coordinate system. And if that's 45, then this is going to be 40. There's 45s all over the place. So I will write it this way. I'm going to write it as cosine of, so let's see, 90 plus 45, 135. So this is a unit vector. If we do cosine comma sine of an angle, that's a unit vector. Cosine sine is a unit vector, right? It gives you something on the unit circle. So this is a unit vector pointing in the direction of 135. Right, from our origin right there, that's 135. So this angle over here is 135 right there. So cosine 135 comma sine 135 is a unit vector that points in the 135 direction. Plus, the right vector has the same magnitude. So now let's form a unit vector that points in its direction. Cosine 45, sine 45. Plus W running out of space. That all equals 0. And again, the 0 that we're talking about is the 0 vector, not the 0 scalar. There is a difference. So this will equal the 0 vector, which is a pair of 0 scalars. Question?
Would it work on the left chain, to do negative cosine?
Yes. Negative cosine 45 is exactly the same as cosine of 135.
Okay.
Absolutely. So in physics, a lot of time they try to use that symmetry, and they'll say, okay, instead of in math, we like to always deal with standard rotation. So we like to think of that angle as 135. Physics people would say, okay, well, the reference angle is 45 degrees, so we could say cosine sine of 45 degrees, but then put a negative in front of the cosine 45 because it's going to the left. Absolutely fine. Totally fine. Okay, so then let's just plug and chug. So we get f times cosine 135, negative root 2 over 2, sine 135. We're going to have a bunch of like terms that we're going to be able to add together. And we're going to put this w vector to the right. So we're going to add it to the right, giving us 0, 500. And in physics also, they tend to just focus on horizontal components all by themselves and then focus on vertical components all by themselves. In math, we like to do it as an equation where we've got, the 2 component vectors all the way across. But either one will get you there. So now we're going to add. We scale by f. So let's do it one step at a time just to make sure that I don't want to skip any steps that might cause you grief. So everyone agree with that? So f is just the number that we've assigned to be the magnitude of the force. It's a number, so it can jump to each component. It can scale that vector. Similarly, over here, we're just going to let that f jump right in. We're scaling the unit vector. And this concept of scaled unit vectors is super important, and it's going to be a very powerful tool to solve lots of problems where we scale a unit vector. Let me even just emphasize that this is a unit vector right here. So that is a unit vector, as is that. So those are scaled unit vectors. Unit vector in the direction of interest multiplied by the magnitude. Now we can combine like terms very easily. So we add the firsts, add the seconds. And if you were doing this from the physics idea where you're just looking at x's and y's, because these angles have the same reference angle, the horizontal components must cancel each other out because that's straight down, and that's reflected right here by having a 0. So our last step is to set our components equal to each other. So we get square root of 2 times f is equal to 500. So that tells us that f is equal to 500 divided by the square root of 2. If you rationalize the denominator, we'll get 250 root 2. So that will be our answer. And the units would be in pounds, not newtons. So each of those cables has to be able to withstand that amount of force so that they're not snapping under the load of 500 pounds. And what can somebody multiply that together? What does that give us?
353.55.
So the idea there is that we're holding a load of 500 pounds with cables that can't even hold the load of 500 pounds themselves. Right? So you've got to be careful when you're stringing loads together. So you can, if you rotate these chains so that they're steeper, you can get away with even using less. The force necessary would be even less to hold up that weight. But if you stretch them out so that angle right there is less than 45, so they're kind of splayed out more, then those chains are you could get to a point where each chain has to be able to hold more than 500 pounds if you have it, splayed out too much. Okay, so any questions on that? Yeah?
Why are those unit vectors exactly? Just the root 2's and root 2's?
How do we determine whether a vector is a unit vector or not? How do we confirm it?
Like I know it's a length 1.
Yeah, exactly. So if you square this, you get 2 over 4.
Right.
If you square that, you get 2 over 4.
Oh, Yahtzee.
Yahtzee! Yahtzee! Oh, yes. Yahtzee. Yahtzee. All right, next section. Time to jump into 3 space. The coordinate system we use in 3 space is the right-handed coordinate system. You can create a left-handed coordinate system. There's some applications for that. 99% of the time, a right-handed system works perfectly fine. So all right-handed means is if you roll your fingers from the x-axis to the y-axis, the z-axis is going to point in the direction of your thumb. So if you go from x to y, z is going to be up. So here we're rolling from x to y, so z is up. If you went from x to y and you wanted a left-hand system, you use your left hand from x to y and z would point down. So we always use a right-hand rule. It's just our convention. So curl our fingers from x to y and z will be in the direction of your thumb. R3. R3 is the collection of all ordered triples. Just like R2 is the collection of all ordered pairs.
Yeah, I've seen some coordinate systems where z is actually horizontal and y goes up.
Yeah, you absolutely can rotate it as long as it follows the right-hand rule. It's totally fine. Some graphing programs will do that, or they'll rotate it for whatever reason.
I've seen a lot of games will do that in their coordinate systems.
Mm-hmm. So if you look at it carefully, it will still follow the right-hand rule, even if z is pointing sideways instead of up. All right, so the R3 space it's got 3 coordinate planes. Just like in R2, you have 2 coordinate lines. R3, you have 3 coordinate planes. Everybody sees those 3 coordinate planes? Can somebody tell me what the equation of the xz plane is? Anyone know what the equation for the xz plane is?
1, 0, 1.
That's a point in that plane, but it's not an equation for that plane.
Y equals some combination of x and z.
Who said that? So when we think about an equation like that, you're defining a relationship then between x, y, and z. So it's got to be even simpler than what you just said.
Y equals 0.
Y equals 0. So if you think about a plane, if we're going to have this xz plane, the idea is that there's no restriction on the x, there's no restriction on the z, but y has to be 0. Let's go back and look at it and at something analogous in 2 dimensions that will make this really obvious. So if we look at a 2-dimensional coordinate system, and we look at the line, the vertical line, let's say, right here, and let's suppose that's the vertical line through 4. So 1, 2, 3, 4. Don't we say that that's x equals 4? So the way we should be thinking about the equation x equals 4, you first off need to know that it's in 2-dimensional space. If somebody says graph x equals 4, the graph's totally different if you're in R1, R2, or R3. In R1, the graph of x equals 4 is just a dot at 4. In R2, the graph of x equals 4 is the set of all points with an x value of 4, and there's no restriction on the y. Y can be anything. Right? Here y is 0, here y is 1, here y is 2, here y is -5, right? So the y can be anything. When you say x is 4, you're talking about all the points where x is 4, and there's no condition on the y. So x equals 4 means all points with x values of 4. So that gives you the vertical line. So if we think back over here, we look, and there's no restriction on the x's and the z's, right? X can be anything in this direction, z can be anything in this direction, but that y value, it has to be 0. So this equation is y equals 0, which implies, again, you need to know, are you in R1, R2, or R3? In R1, that's just a dot at 0 on the y-axis. In R2, y equals 0 is the x-axis. In R3, it's the xy plane. Excuse me, xz plane. Y equals 0 is the xz plane. So that says that all ordered triples with a y value of 0. So x could be 5, z could be 5, but y has to be 0. That makes sense? How about the other 2 planes? If we wanted to come up with the equation for the yz plane, it has to be?
X equals 0.
Yeah, x equals 0. That's going to give us that one. And if we wanted the xy plane, we'll get zb0. 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 Yes. Day 1. Got to get the stamina back. Got to get the drive back. Okay, so and over here, x equals 4, if we said the graph was in R3, that would say all ordered triples with an x value of 4. Y can be anything, z can be anything. So can you visualize that over here? So we'd have to be coming out in the positive x direction, 4 units. And we want the plane that goes through there, which is very difficult to draw, but can you visualize it? So it's parallel to the green plane, but out here at 4. That would be the set of all ordered triples with x being 4. No restriction on the y. If that plane's right here, you can go y as much as you want. And then z, same thing, no restriction. You can go up or down as far as you want. So x equals 4 would be a plane parallel to the yz plane. Takes a little practice. there is a great piece of software that I used to use a lot for other purposes, for two-dimensional stuff, and then they released Desmos, and most of you have seen Desmos. Desmos is a really nice piece of free graphing software for anything in 2 dimensions. Desmos.com, click on graphing, and graphs beautifully. And the old school one that I used to use for 2-dimensional graphing is a little more complicated than Desmos. GeoGebra, combination of geometry and algebra, they released their 3D grapher just a couple years ago, and it's really good now. It's very, very good. If we have time at the end, I'll pull it up at some point. You can graph planes and play around, graph all sorts of things. You can graph all sorts of surfaces. It shows intersections really nicely. It's super cool. All right, let's go to the next slide. So this is for 3D graphing. And this is for 2D, and it also does all sorts of algebra stuff nicely as well. Did I jump a slide? No. Okay. All right. So here they're kind of showing us our basic planes. So whenever we have a new coordinate system, whether it's rectangular, which you've done for many years, in Calc 2 you were introduced to the polar coordinate system. So you typically want to look at the basic equations, and by basic equation we mean take your coordinate variable and set it to a constant. What's the graph? So here we're still in rectangular, but we're in 3D, so we just want to check. What does x equal a constant look like? Y equal a constant? Z equal a constant? In polar, the two coordinates are r and theta. And if r is a constant, r equals 4 in polar gives you a circle of radius 4 centered at the origin. And if theta was a constant, it gives you a line tilted through the origin in polar. We'll get to that later. We're going to do a lot of polar in a couple chapters. Okay, so this makes sense. Can you visualize how x equals a constant is parallel to the yz plane, y equals a constant is parallel to the xz plane, and then z equals a constant parallel to the xy plane? All right. So now we want to find the equation of the plane that passes through those 3 points right there. The plane that passes through these 3 points. So there's a few ways to find the equation of a plane. And let me just check one thing before I get, because we have not done. So the way we will find the equation of a plane in general, in a couple more sections, is a little bit different. Let me just mention it though. If you have a plane, an important thing to the plane is a vector that's perpendicular to it. It's kind of like the handle on it. It's called the normal vector to it, and we can use that normal vector to find the equation of that plane pretty easily. Okay. So that's going to be in general the way that we're going to do it in the long run. So the question here is a little bit more vague. We don't quite use that general approach. Can anyone sort of see if we draw a picture here? Let's see if we can piece it together. So we're going to have a plane, this point right here. So we're going to call this the x-axis, that's the y-axis, that's the z-axis. So we're going to go through 2, 0. And then 0, 3, 0. It's going to be right there. Oh, you know what? I don't have my book in front of me. I don't think that this is asking for the equation of the plane.
Graphing it?
I think that's what it's asking. Does someone have their book there? Can you look at number 19?
Oh, in the back.
Yeah, just see what the instructions are. Sometimes it's a bad habit to just put the
It
problem
says
up.
sketch it.
Okay.
That's
All
all it wants to do.
All right, I was starting to panic there. I was like, wait a minute, we don't know how to do normal vectors yet. That makes it a little harder. Thank you, yeah. So not putting the instructions is a little dangerous. This is a plane that is easily intuited. If you look at it, you can see, oh yeah, that face that intersects the first octant. when we talk about the three-dimensional coordinate system, we talk about octants. The only one that has a name is the first octant. So instead of quadrants like you have in a Cartesian system, in a two-dimensional system where you have quadrant 1, 2, 3, 4, with a three-dimensional system, you're going to have 8 octants, 4 kind of up top, 4 down below. The only one that has a name is octant 1, and that's where x, y, and z are all positive. It's the one you can graph most easily. The one you see here is octant 1. And you can see that the intersection of this plane in octant 1, you get this triangle, it kind of forms a tetrahedron. But you can kind of imagine the plane tilting and going on forever. But just drawing, if it tilts into quadrant 1 like that, you can at least get a visual kind of how it looks. But yeah, so we will find the equation of this plane shortly, but not quite yet. Not yet. Okay. All right, we already did this, but we did something similar to it. Let's just do that quickly. So x equals 2, again, it's the set of all ordered triples. We're assuming that we're dealing with an ambient space of R3. So the space in which our objects are living is R3. X equals 2, set of all triples where x is 2 and y and z have no restriction. So I think the easiest way to draw these things is sort of putting maybe like that. That's not too bad. Or maybe we should even put it the other direction. I don't know. I don't know what the best way is. There, plane. So x equals 2, there's x equals 1, there's x equals 2.
So we only want the corner of it on the...
Yeah, it's usually what they try to do just to sort of, so it doesn't get super messy. And if you try to draw it so that that mark there is in the middle of it, then you can't tell where it is with respect to the axis. So
That's what I was doing for a second.
yeah, which is very tempting. It's very, you want to do something like that. And then it's harder to,
I was like,
I want to get fancy.
it's harder to tell. But if you just,
I was like, wait a minute.
if you touch one corner to it, it becomes a little bit more obvious. So again, that's a point where x is 2, y, z, or whatever.
Oh, technically that plane is extending forever in y and z directions.
Yes, all directions, yeah. Well, yes. What you said, y and z directions, all, yes, not all directions, in those two directions. All right, distances in R3. Again, if you're dealing with vectors in R3, all you have to do is add a third term. Oh, wait, that's, what's going on here? Distances in R3. No, there it is. So all we're going to do is add this third term here. So that third term gets added. So if we have a vector with 3 components, we still do sum of squares and then take the square root. It's just that we have a third component. And here they're geometrically showing that the distance from there to there, you can build up to it by doing an extension of what happens in two-dimensional space. So if we have 2 points in three-dimensional space, the distance between those 3 points, same thing. Square root, sum of squares, we have 1 extra displacement. Have to take the change in x, have to take the change in y, have to take the change in z. So 1 extra term. Same with the midpoint. You know that in two-dimensional space, you would just have those first 2 components. Three-dimensional space, you have to also average the z coordinates. So you average the x's, average the y's, average the z's to get the middle point. Oh, I guess I'm still a rectangle. Okay, so pretty intuitive for midpoint there. Averaging coordinates. Go down, there we go. All right, so if we want the distance between these 2 points, we're going to say that the distance is equal to the square root of the sum of the squares of the differences of the corresponding coordinates. So change in x, change in y, change in z, square them. So 5 minus minus 1, 0 minus minus 2, negative 2 minus 3 is negative 1. And square.
5.
So 41, square root of 41.
-5.
Question?
-2 minus 3 will be -5.
So we're subtracting the y's from the y's. the x's from the x,
And
the
z.
z from the z.
So -2.
So 5 minus minus 1 is 6. 0 minus minus 2 is 2. -2 minus 3 is -1. -2 minus 3 is -1. Did I say that right?
No.
That didn't sound right.
Oh.
-2 minus 3 is -5. Holy cow. Who knew arithmetic was so hard? -2 minus 3. -2 minus 3. -5. Oh, gosh.
Thank you, Hung.
Yeah. Just making sure Hung's awake. So what does that all add to, like 65 then? 40, 65. And I think that that's not, right, 13 times 5? So, yeah. So that would be the distance between the 2 points. Assuming we subtracted correctly. All right, midpoint. Here we have to average, so 5 minus 1 is 4. We average those 2 points, those 2 coordinates by dividing by 2. We add the next 2. 0 plus -2 is -2 divided by 2. Add those 2, and we get 1, 2. So our midpoint is going to be the ordered triple 2, -1, 1/2. That will be our midpoint. All right. Any questions on that idea? And so in linear algebra, you just do this with 4, 5, 6, 7. You just keep on adding extra components, and it works out just fine. So you'll have to come in linear algebra. You come up with a notation because you don't want to be writing out an infinite number of components. So you come up with some cool notation to take care of that ... stuff. All right, we need to know the difference between a sphere and a ball. In math, a sphere is hollow, but a ball is solid, like a pool ball. Pool, like the game, the billiards ball. So, sphere is just the edge of a ball, and you all have seen, I think, the equation of a sphere before. This is the sphere center ABC with a radius of r. And then if we want the ball, we have to turn it into an inequality because we're not just talking about the surface, we're talking about all the points on the inside. So the ball is going to be the points that have a radius less than or equal to r squared. That would fill it all in. So we've got a solid ball. Okay. And then here it says find the equation of a sphere that has that center with that radius. So go ahead. Write down that sphere. Write down that sphere's equation. Better than that. Write down the equation of that sphere.
Sounds like a game show. Write that sphere.
Bless you. What's that?
He said it's like a game show. Write down that sphere.
Write down that sphere.
One of those kids in that Junior Genius thing.
Yeah.
You were so-
Yeah, those guys are. Some of those kids are crazy. Makes me sick. I'm not smarter than a 5th grader.
Nope.
Okay, neither is Paula Dean, so you're okay.
Oh, gee, thanks.
What?
She was on that show at one point.
So, all she knows about
Deep
is
frying Twinkies.
butter.
Yes.
The South. So the radius will be squared on the right. So we're going to look at this equation up here. So if the radius is 5, we'll have 25 on the right. And then it's always going to be x minus the x coordinate of the center, y minus the y coordinate. So yeah, it's kind of like the equation of a circle with one extra term in it. So the form of this equation will end up being.
Do you want us to multiply it out?
No. Yeah. Yeah.
I'm gonna hit you.
Yeah. No, don't do that.
Please.
Please don't do that. Yeah. So that'll be our equation. We'll call that standard form. Standard form typically means that you can see important characteristics of the object. So standard form for a sphere, you can see the radius, you can see the center right there. If you multiply it all out, that's called general form, and usually general form you can't quite see the important characteristics. So factored form is totally fine, or whatever. Standard form is totally fine. All right, let's see if we can, this one looks a little weird. The first thing we see is that we're less than or equal to, so we know that if the object is not degenerate, if there's actually solutions, that we're probably dealing with a ball and not a sphere. Zip tie is snapped. But we can't quite see the important characteristics of this object on the left. We're assuming it's probably, if we look here and think of this as an equal sign, we're probably thinking this is a sphere. Let's try. What would we do with the y's to make this work?
Complete square.
Yeah, complete the square. So we take the coefficient of y, divide by 2, and square. So we would have to add 49 right here, divide the 14 by 2, and square it. Let's see, that seems to be z. And then, of course, we have to add it to the right also to preserve the inequality, I guess, in this case. Preserve the inequality. This doesn't sound right. Let's preserve the inequality. So then we can factor on the left. And when we do that, the right-hand side becomes positive, which is good. So now we see that we are, in fact, dealing with a ball and not some degenerate object that has no solutions. So what would we say? What's the center of this ball?
070.
Yeah, exactly. 070. Whoops. Ball with center 070. 070. And radius 6. Yep. So completing the square. Start blowing out some cobwebs. Completing the square. Maybe we should do some integration by parts.
It's Halloween, man. Why are you blowing out cobwebs?
We'll need a compressor.
I like it.
All right. Magnitude of the vector from point to point. Not too bad. First, let's do the displacement vector. We don't have a ton of time, so let's go through these ones. So what's the first component of this vector? 3 minus 5 is 3 plus 5, so that's 8. Next component. So we're doing the terminal point minus the initial point. So terminal point minus the initial point. So it's saying from -5, 0, 2, so that tells us that's the initial point. So that's our displacement vector that connects those 2 points. And then if we want the magnitude of that vector, the magnitude of v, so now we're in 3 dimensions, so all we have to do is add 1 extra term. We square, 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 get the square root of 74. And that's prime enough. Has no perfect squares in it. Relatively prime. All right, so then find the displacement vector from there to there. So same idea. We're going to subtract, we already did it. That's what we did up there. Why did I do this a second time? I'm not sure yet. Just to change and compare component form to algebraic form. If we're in 3 space, we have an extra term. So this would be 8i plus j minus 3k. So that would be the algebraic form. Yeah?
Do we need the arrows for the algebraic form over there?
Yes, because you can't indicate on your paper, a vector is represented by a bold character. And so if you're writing it by hand, we put the little arrow over it because we can't really I mean, if you're clever with markers and things, you could probably do it without.
Sure.
It's the same as doing the hat, right?
Yeah, same as doing the hat. Yeah, absolutely.
Isn't
Same
that
as doing the hat.
Hat's unit vector, isn't it?
These are unit vectors.
Okay.
Yeah, ij and k are all unit vectors.
I am everywhere.
Yeah. Yes, hats, whatever. All right, we'll stop here. We'll do these two. When we meet again on Wednesday. So go ahead, read the syllabus, look at the course layout and everything. If you have any questions, come and see me, email me, come to the Mass Center, send a carrier pigeon. You can bring your daughter, you can bring your dog.
I only have a
Sorry,
daughter.
joking.
I only have a daughter, but I will bring her on Mondays if I can.
Can I bring my sister?
How old is she?
10.
Sure.
She can hang out with my 5-year-old.
She's old enough to do a little math. We can ask her some math
We
questions.
can have them go play together while we do math.
How old is your daughter now?
She just turned 5 in
Five.
July. Yeah.
Five.
She's making me old.
Do you have office hours today?
Yeah. Sick. Go do math right
Today is
away.
the only day I get to be here.
Oh, what's up?
Every other